G'day, welcome to video one of a video series on exponential and logarithmic functions. We're looking first at graphs of exponential functions, but first we'll have a look at a special symbol by the name of E. E is an irrational number, a bit like pi. It's a special number with a special property, and that special number has a property for which the differentiation of e to the x is e to the x. So it's the only term really, e to the x, whereby the differentiation of the value ends up not changing it. The differentiation of e to the x is still e to the x. Now it's approximately equal to 2.71828. That value of e can be gotten on your calculator by pressing e to the x to the and putting 1 in as the x value. So above your button on your calculator that looks like an ln, it has an e to the x. So if you press shift ln 1 equals, you should get that 2.71828 value. But we're working with the number e in a special way for differentiation because of that special property. Okay, let's have a look at the graph of a curve y equals e to the power of x. And there's three special things that occur. It's like any other graph of an exponential. Graphs of y equals 2 to the x or y equals 3 to the x look very similar to this one. And it's got three main features to it, an exponential graph. Let's have a look at them one at a time. The first feature, it has what we call an asymptote. Funny sort of word. But an asymptote situation is a situation where a curve, the curve in green, gets closer and closer, as you can see here, to a line, in this case the x-axis. The green curve gets closer and closer to the x-axis without ever touching it. So we say that this curve here, y equals e to the power of x, has an asymptote on the negative x-axis. This is where the x-axis has its negative values all the way along here. So it's got an asymptote situation there. That's one of the features of any exponential graph. Another feature is through your basic y equals e to the x curve always has a y-intercept of 1. Now the reason for that is there's a special thing that happens on the y-axis here, and that is that all along the y-axis we have an x value of 0. And because we've got the curve y equals e to the x, what we'll get for our y, if we subbed in an x value of 0, we'd get e to the 0. And anything to the 0 we know has a value of 1. You know, 2 to the 0 equals 1, 5 to the 0 equals 1. So by rights, e to the 0 should equal 1 as well. So that's how we always get a y-intercept of 1 for your basic exponential curve. Now, third sort of property or feature of our y equals e to the x graph is that it increases what we call exponentially. We use this word in plain English to describe something such as, some people might say, the population in China is increasing exponentially. It means it's going through the roof and increasing rapidly. So in this circle bit here, the idea that that green curve goes up very, very quickly is an exponential idea. So there's three features of y equals e to the x as a curve. Now we'll just have a look at a couple of variations of that. We have similar shapes here, but slightly different things are happening because slightly different things are happening to the curve. Here we have in this first one, y equals 2 plus e to the x. Now you'll notice it has exactly the same shape as our y equals e to the x, but it's been moved up 2 units. Now because it's moved up 2 units, instead of a y-intercept at 1, we have a y-intercept of 3. And instead of an asymptote along the x-axis that we had for our basic curve, that asymptote line has moved up 2 as well. So within this one, we've got an asymptote for the line y equals 2, not the line y equals 0. So the effect of having a 2 added to our basic e to the x moves the whole curve up 2 units. Now here, what's the effect of having a minus, or a -1 really, in front of the power? Well, you can see that that's kind of mirror reversed the usual y equals e to the x curve around the y-axis. So where the asymptote used to be on this side, it's now on this side. Where the exponential used to be up here, it's now up here. We've still kept the y-intercept of 1 though. And a -1 out the front of our basic curve, what effect has that had? Well, what effect it has had is it's got a mirror reverse sort of situation. It's reflected around the x-axis here. And where the basic curve used to go up like that, it's been reversed and reflected on the x-axis, so we've got that shape going down here. You'll notice our y-intercept has gone from having a 1 as our y-intercept to a -1 as our y-intercept. So just some slight variations from the basic theme of y equals e to the x, depending whether there was a +2, a -1 on the indices section, or a -1 out the front. So just some basic variations there. Okay, now finding values using e to the x. I hinted at this ln button, or shift ln process before on the first page there when I was talking about the value of e. If we have to evaluate something like 3 times e to the 0.7, we'll use that process again. 3 times bit, these are the pressings on our calculator here. This is fairly obvious, this first bit. 3 times, shift ln will get that e to the x thing happening. Then we'll put in as an x value 0.7 and press equals. And if you're doing it like me, you will probably get a value along the lines of 6.041258122 for that 3e to the 0.7 question. And we might have to round it off according to what they want in the question. They might say it round it off to 3 decimal places or whatever. We can respond to that too. So that's how we answer some questions where we're asked for values of e to the something or other. Okay, we've introduced a new concept of e. It's a value for which e to the x differentiated is still e to the x, and we're working closely with graphs of that and values of that as well. Hope that's an introduction to the exponential idea, and see you next time. Bye.